we are going to start with this question, exercise 5.1, question number 30, and this is the most important question of this exercise. See, this question, you have to find values of a and b such that the function defined by this is continuous. It means this function is continuous throughout. Now you have to find two variables a and b. It is very clear that you should have at least two relations depicting a and b, depicted by a and b. So we'll try to find two solutions. So how can we do this? There are 2 points at which we can find that we can use that function is continuous at x equal to 2 and at x equal to 10. So let's start with this. We can start this way. At x equal to 2, f is continuous. So it means if f is continuous, then left hand limit and right hand limit both will exist, and we can write this like this way: left hand limit, this is limit h tends to 0, f2 minus h. This f2 minus h is this value 2 minus h is less than 2. So for less than 2, your fx is 5. So whatever you put h equal to 0 something, you will get answer as 5. Now come to the right hand limit. Right hand limit is limit h tends to 0, and this is f2 plus h. So now f2 plus h means your this 2 plus h is greater than 2. If it is greater than 2, then this is coming into this ax plus b, but that x has to be replaced by 2 plus h. So this is a 2 plus h, and this is b. So put the limit, so you will get 2a plus b. So this is your relation 1, this is your relation 2, this is your equation 1, this is your equation 2. You know that the function left hand limit and right hand limit will be equal. So though it's equal to the value of the function at that point, so that is 2 again. So there is no need to find again that value of the function at x equal to 2. So we can use this. So this relation implies that 2a plus b equal to 5. Mark this relation as 1. Now we again use that at x equal to 10, f is continuous. So we can use left hand limit at x equal to this 10. So this is h tends to 0, f 10 minus h. So this 10 minus h is x is this number 10 minus h is less than 10. So this less than 10, it means the value of the function will be ax plus b, but h has to be, this x has to be replaced by 10 minus h. So this becomes a 10 minus h plus b. So you are going to get, after this you put the value, so you are going to get this 10a plus b. Now come to the right hand limit. Right hand limit will be limit h tends to 0, f 10 plus h. So this is limit h tends to 0, and f10 plus h, you can see f10 plus h means greater than 10. If fx is greater if x is greater than 10, then value of the function is 21. So you can write here 21. So answer is 21. So from again we know that left hand limit equal to right hand limit exists always. So you are getting 10a plus b equal to 21. Now we have got these two relations. We'll solve them by using any of the method you can use. So solve 1 and 2. So you are going to get 2a plus b equal to 5 and 10a plus b equal to 21. You find the difference. This is minus, and this is minus. So this is minus 8a. This bb will get cancelled. This is minus 16. So a is going to be 2. Now put a equal to 2 in 1. So you are going to get 2 into 2 plus b equal to 5. So b is going to be 1. Therefore a equal to 2 and b equal to 1 is your answer. We now start the topic differentiability of the function. Now we have find the derivatives of the function in class 11th, but just I am recapitulating what we did in class 11th. So with the help of example I start that if y equal to x square you take, now y equal to x square, you know, this is the parabola, and this parabola will be looking like this, and this is y equal to x square. So now when I ask you to differentiate, you do the differentiation as dy by dx equal to 2x. So I explained this in class 11th also, but what that 2x means. So if you know this, then this is really good. If you don't know, just listen this, how what I'm going to explain. This derivative means that this function is differentiable, and the value of the differentiations, function, if you differentiate, that is coming as 2x. I have applied the this power rule. Now if I dy by dx, if I take x equal to 1, then this will be 2 into 1 equal to 2. So what does it mean? What that 2 is showing us? It means that if I take this, let's say this is x equal to 1, and if I, this is the point of intersection of this x equal to 1, and this is the graph. So it means simple is, if I want to draw the tangent at this point, so you can see this, I'm using this different color so that you can differentiate. So if I'm drawing this tangent at x equal to 1, so the slope of this tangent, the slope of the tangent is 2. So that is what you get when you differentiate the function. Similarly, if you put x equal to 2, then you will get a tangent at this point, and whose slope will be this 2 into 2, the value of the slope will be 4. So this shows us, like, the function, if it is differentiable, you can put the value of the function of x, and you will get the slope of the tangent at that point. But this is not the case that always you can put any value. There are some restrictions on that you have to see. For example, if I take y equal to x minus 1, and this is let's say this is minus 2, and if I differentiate, then dy by dx will be minus 2 x minus 1, and this is minus 3, so that you can do x minus 1 whole cube. Now we have got the differentiation of the function, but what does it mean? Can I get the tangent of this function everywhere? No, this function's tangent cannot be defined at x equal to 1. So tangent cannot be drawn at x equal to 1, because if you put x equal to 1, that this function will become not defined. Or you can say this way also, if you draw the tangent, then the slope of the tangent will be this perpendicular way, it will be coming, because 1090 is not defined. So this way you can say tangent cannot be drawn at that point x equal to 1. So just keep in mind that this differentiation should always be defined for whatever value you substitute. So now we move to the geometrical or graphical meaning of differentiability that we did in class 11th, and now we are revising that again. Now let's say this is some function. This function is, let's say this is fx. I'm using this pen so that because points will be very close and it will be difficult to draw with the help of a marker. So now you see this point is your C, and this value at this point will be fc. And this point will be C comma fc. Now take another point here, this but this is very close to that point C, and I'm taking that point as C plus h. This is C plus h. So here the value of this coordinate will be C plus h f C plus h. This is C plus h and minus comma f C plus h. You can see this. I'm making it more closer so that you can watch this very clearly. So this is C comma fc, and this point is C plus h comma fc plus h. Now I can you can see if I want to draw the line segment, you say this is the line segment that I'm drawing, and this point we can also say this point as A, this point as B. So that AB is a secant of the tangent or secant of this graph. So we can find the slope of this secant. So you see the slope of secant will be f. I can write this f c plus h minus fc upon c plus h minus c. So I can just recall you the formula of finding slope. It is y2 minus y1 upon x2 minus x1. So here your y2 is fc plus h and y1 is fc. So difference of this is the slope of the tangent. Now, so no, sorry, this is the slope of the secant AB. This is slope of AB, and AB is a secant. And similarly we can also take some point. Let's say this point I'm taking here, this is C, and I'm joining this A to C, and let's say this point is C minus H. The points are very close to each other, C and C minus H, they are not very far, because but I have made I made them far so that you can see the difference. So this coordinate will be C minus H comma F C minus H. So now if I want to write the slope of AC, then I can write this this point we can mark as let's say this point as AB, and we can say take this point as capital D. So slope of AD will be, you can see the formula, that FC minus H minus FC upon C minus H minus C. So this is the slope of AD and this is the slope of AB. Now, but you have to see one important thing, that if I reduce that value of H and I make this value as 0, then what happens? You see this I can use something else now. This is the scale that this is on AB. You can see this is on AB. So for the time being, this is a secant, right? Because this is meeting this curve at 2 points AB, but this will slowly and gradually come. B will get shifted to A if I make H tends to 0. Means if H is becoming small, then this gap will be reducing and at when that C plus H will come to C, or if I say that B will come to A, then this secant will become your tangent, and this line will be coming here. So this will be your tangent at point A. So that slope of AB will become slope of tangent at A. So but I have to apply this slope of tangent. I can write, or I can simply write this dy by dx at A. We can get this slope when I make that limit h tends to 0, fc plus h minus fc upon h. So this derivative is called right hand derivative. So this also you can say right hand derivative. This is limit h tends to 0, fc plus h minus fc upon h. So this is called the left hand right hand derivative. Similarly, this AD is a secant. Now this AD is a secant. I can use something else also. This AD is a secant. You can see this AD is a secant. Now if this D, or I say then if I make C tends to 0, then this D point will come closer and closer, and thus D will come on A if H is going to be 0. So it means that this slope of AD will become the slope of tangent, or you can say dy by dx if I take limit h tends to 0, fc minus h minus fc upon minus h. So this is actually your left hand derivative. So limit, this is h tends to 0, fc minus h minus fc upon minus h. So now you have seen that what left hand derivative is and what right hand derivative is. So we can now further will say function is differentiable at point A if left hand derivative and right hand derivatives are equal. So function f has derivative, f has unique tangent, you can say unique tangent also at A if left hand derivative equal to right hand derivative. See, in class 11th you did not get any function which was not differentiable. In class 11th every function was differentiable, that's why we did not discuss this left hand derivative, we did only right hand derivative. But now the question has come to us, or we are going to verify whether the function is differentiable at the given point or not. So we have to now check that left hand derivative and right hand derivative should be equal, because this time we are going to check. In class 11th it was given to you that they were differentiable. Now you see this theorem number 3. This is a very important result, that if function f is differentiable at a point C, let's say this point is C, then it is also continuous at that point. But converse is not true. So basically we are going to discuss this part first, that function is differentiable, then it is continuous at the same point. So we'll write that first. What is given to us? Given is f is differentiable at C. It means that limit x tends to C, fx minus fc upon x minus c, this is equal to f dash c. So this is given to us, and we have to show that f is continuous. So it means that we have to show that limit x tends to c, fx is equal to f of c. So we can give the proof. Here x not equal to c, we have to assume this in the beginning. So now I can write this fx minus fc, fx minus fc, I divide by this and multiply by this x minus c. And after this I can take limit on both sides. So if I take limit on both sides, then limit x tends to c, fx minus fc, and here also if I take limit x tends to c, then you take fx minus fc upon x minus c into limit x tends to c, and this is x minus c. So we'll open this can be written as limit x tends to c fx, and this will be because x tends to c, so this is already fc, this is some constant value, and now this is, it's given to you, this is f dash c, and if you put this x tends to c, then this will become 0. So ultimately this side will be 0. So your answer now has come that fx is equal to fc. It means f is continuous. Now next, if I just the converse also see that every means if f is differentiable, then it has to be continuous at that point. But if it is like continuous, it is not necessary that it will be differentiable. So for example, let fx equal to mod x. So just I'm going to discuss this orally, that at this function is continuous throughout, because you can see there is no gap. If you want to draw the graph of this function will be this. So there is no gap, this is the continuous function, and you can prove that also it is a continuous function. But it is not differentiable, and basically it is not differentiable at that point x you can check whether at any point, random point you take, and you will find that left hand derivative and right hand derivative will not be equal. So this is the converse that you can show, and this is most important type also, because most of the time in competitive exams or in some of the other exams, they ask the function, give the example of a function which is continuous but not differentiable. So that time you can give the example of this function. You please try this yourself. It's also given in ncert book. You can see the proof of that also, but that is very quite obvious. You can see that you are not going to get unique tangent. See, I told you that unique tangent I written in the previous differentiability video. In this previous I explained you that at point A you must get the unique tangent. So at this point you are not going to unique tangent, because one tangent will be like this and one tangent will be like this. There will be two tangents at that point. So this function is not differentiable. Rest you see the problem in the ncert. Now to discuss something more about differentiability, that we are taking this example, this question number 9 of exercise 5.2. You have to show that this function is not differentiable at x equal to 1. You know that this function is continuous everywhere. This is a modulus function, and modulus functions are continuous everywhere. Now, but that you inside you see, if you put this part equal to 0, then x will be equal to 1. So it means that at x equal to 1, you are not going to get unique tangent. So this will not be differentiable at that point. Now, but we have to show this through this algebraic method. First we find the left hand derivative at x equal to 1. So you see the formula. I've written the formula for general point C. Then you take C minus H fc, and this is left hand derivative, right hand derivative C plus H minus fc upon H. And I'm now taking left hand derivative first. So this formula I've used here. Now you substitute the values. So value of this will be limit h tends to 0. This will be 1 minus h minus 1. I am replacing x by 1 minus h. So this is the one, and the next one is f1. So f1 is 1 minus 1, and you may write this denominator as h. So now you may put the value of this h tends to 0, but you see first you have to simplify this. So you can see this can be cancelled, this 1 and this 1 can be cancelled. So this is 0. So now it will be minus mod h, and this is 0 upon h, and this is limit h tends to 0. So this, you know that h is positive number, so negative of sign will become positive. So this will become h upon h, and this limit h tends to 0. So answer is 1. So now we'll calculate right hand derivative. So now applying the formula directly, limit h tends to 0. This is 1 plus h minus 1, as you can see there, and this is now f at 1. So this is again 1 minus 1. This is your minus h. So this was your minus h. So this is your plus h. So answer of this was minus 1. So this is minus h. We can make it with this color so that you can understand the difference. This is minus h, so that value was minus 1. Now we simplify this. So 1 will get cancelled by 1, this 1 will get cancelled by 1, and this is 0. So this is going to be limit h tends to 0, and this is mod h minus 0 upon h. So mod h upon h will be h. So you see limit h tends to 0, this is h, and this is upon h. So answer is going to be 1. So you can see that left hand derivative not equal to right hand derivative. So f is not, therefore f is not differentiable at x equal to 1. Now we'll discuss this question number 10. This show that fx equal to greatest integer function where x is lying between 0 to 3 is not differentiable at x equal to 1 and x equal to 2. This is the greatest integer function, and you done this greatest integer function. I'm just explaining you again. If it is 2.1, the answer will be 2. So we go towards left side on the number line, and whatever integers we get first, we get the answer of this greatest integer function. So we have to show that it is not differentiable at x equal to 1 and x equal to 2. So I'm doing for x equal to 1. You see that left hand derivative will write first, limit h tends to 0. This is will be 1 minus h minus f1 upon minus h. So put this value, limit h tends to 0, f1 minus h will be 1 minus h, this is greatest integer function, and this is 1, and this is upon minus h. So you see 1 minus h means you are subtracting some small number from 1. So it will be, for example, it will become like 0.9. So 0.9 is equal to this 0. So this is 0, h tends to 0, and f1 is 1, and this is minus h. So you can see if I, so now after solving it, you are getting 0 minus 1 and minus h. So you can see when you put h tends to 0, this is not defined. So you can see this is not defined. Now find right hand derivative, limit h tends to 0. I'm applying the formula. This is 1 plus h minus f1. f1 means this is greatest integer function I should write, but next step I'll write this. So this is limit h tends to 0, 1 plus h minus 1 upon h. So you know this 1 plus h means 1.1 something, and this is equal to now 1. So this will be limit h tends to 0, and this will become 1, and this is again 1 upon h. So this is limit h tends to 0, 0 upon h. So answer of this will be 0. So 0 function divided by any function is 0. You can see that left hand derivative not equal to right hand derivative. So f is not different.